This is lecture 13. So in the previous lecture, we were looking into what happens to the condition of a common source amplifier, right? When the signal at its input swings, right? So by the way, let me take a moment to emphasize the fact that, so what is the configuration of the amplifier, potential amplifier that we were interested in? So this is the gate, this is the drain, and this is the source. So the input is incrementally, what is the incremental equivalent of this? Incremental equivalent of this structure is so you have the gate, right? So what I'll do is I will sketch the MOSFET, I will sketch this entire structure, and then show you the incremental equivalent. So what should you do in order to get the incremental equivalent? So you should first replace the nonlinear device with its linearized equivalent. And what is the linearized equivalent of this MOSFET M1? So the linearized the linearized equivalent of this MOSFET is nothing but a current control source whose controlling terminal are the gate and the source, correct? The constant voltage sources go to 0, so this shorts. We leave the incremental voltage source as is. On the output side, the constant voltage source goes to 0, right? And what is the other terminal? This is the drain terminal, and this connects to RL. What is the value of this control source? The value of this control source is GM times VGS, right? Okay. So incrementally, if you see, the input is applied between the gate and the source, right? And the output, where are we taking the output? The output is taken between another terminal, which is drain in this case, and the source, right? So the common terminal between the input and the output is the source terminal, and since the common terminal in the incremental model is a source terminal, it's called a common source configuration, right? So this is also called common source amplifier, right? So Another way of thinking, another way to think of it is the fact that whenever we say whenever we say common, right, you will see several configurations which that we'll be dealing with in the upcoming lectures. This common term will come. You will see common source, common gate, common drain, and so on. So this common, essentially, in your mind, at the back of your mind, you can replace common as grounded source, right? You can say that this is almost equivalent to saying you have a grounded source configuration. Okay. I find this terminology a bit more useful because it's much more general while dealing with other configurations as well, right? So, however, in the literature, common source amplifier is a generic term, so we will refer to this configuration as common source amplifier. But at the back of your mind, you should have the understanding that whenever we are saying common source amplifier, we are essentially pointing to the fact that the source is incrementally grounded. Okay, great. And also, it's not only the source is incrementally grounded, it should be common. The input should have been applied between between the gate and the incrementally grounded source, and the drain. The output is also between some other terminal and the grounded source. Okay, fine. So now so now in the previous lecture we were delving into what happens when the signal actually swings, right? So it is one matter to just apply the voltages, the quiescent voltages, and set up the quiescent currents in order to keep the transistor in saturation. But it's a different ball game altogether when we say that transistor should be in saturation even when I apply an incremental input, right? And when we saw that in case of this particular configuration, or if we saw that if incrementally my input, if Vi is, or even if I say that incrementally if this is the VGS, and assuming the transistor is in saturation, right? So subtext is transistor is in saturation. We saw that there were two conditions that we needed to maintain, right? What were the two conditions? So this is gate, this is drain, this is source. The primary condition that we had to maintain was, for saturation, the total drain voltage Vd had to be greater than equal to the total gate voltage Vg minus the threshold voltage, right? Okay. In other words, if I have to break it down, what is total drain voltage? Total drain voltage is nothing but the quiescent drain voltage, VDQ, or capital V, capital D, right, plus the incremental drain voltage should be greater than the total gate voltage, right, minus the threshold voltage. So this was the saturation region. This condition we had to ensure in order to make sure that the transistor always remains in saturation. What was the second condition? The second condition was to ensure the transistor is sufficiently on right? So when we say the transistor is sufficiently on, what are we implying? We are implying that we know that the VGS, when the VGS swings, it can go up or it can go down. When VGS goes up, right? When VGS goes up, I run into a potential problem of the transistor going out of saturation, because the drain voltage because I am closing the gap between the gate and the drain, right? However, when the VGS goes down, when the VGS goes in this half cycle, when the VGS goes down, what is the likely cause of problem? The likely potential problematic cause is the transistor can get into cutoff, right? And we did the analysis and we saw that we had to ensure that the incremental VGS, right, had to be much less than what? Twice the overdrive of the transistor, right? Twice the quiescent overdrive of the transistor. Correct? And if we, in a common source configuration, if I go to this common source configuration, what is this incremental VGS? Yeah, incremental VGS is, so in common source configuration, this incremental VGS is the input that has been applied directly, right? And if I say that the input is sinusoid, right, if the input is sinusoid, then VGS essentially becomes Vp sin omega naught t, right? So what is the condition on Vp? What is the condition on Vp to ensure that the transistor or the small signal approximation always holds? So let me take a step back, and I think I should rephrase this statement. So if we go back to the previous lecture, we saw that this condition was required in order to ensure the validity of the small signal approximation, regardless of whether the signal is swinging on top or swinging to the positive cycle or in the negative cycle, right? So let me correct myself here. So the condition that I am referring to here is to ensure validity of small signal approximation, we have to ensure this VGS is much less than twice the overdrive, right? We'll come to what is the condition, what is the minimum VGS that we can apply shortly. But again, I mean, this is a correction, right, from the statement that I had made 2 minutes back, that this condition is to ensure the validity of the small signal approximation. So in a common source amplifier, VGS essentially is equal to Vi, which is equal to Vp sin omega naught t, right? Since this is that case, so what is the maximum Vp that you can apply in order to ensure the small signal validity, right? The small signal approximation is still valid. Note that when you have the sinusoid Vp sin omega t, the sinusoid goes on either direction, and this peak to peak is twice Vp, right? Which means VGS max is twice Vp, which means you have to ensure Vp is less than 1 overdrive. So in a common source configuration, right, you have to ensure that the sinusoid that you have applied is much less than the overdrive of the transistor. And if you are not particularly bothered about whether it's a common source configuration or not, right, then the question arises, how should I, let's say I have a network which has a transistor where whole bunch of stuffs are connected to the source, whole bunch of stuffs are connected to the gate, and whole bunch of stuffs are connected to the drain, right? Then how do I know what is the constraint? What is the constraint for small signal approximation? That is a quite a valid question to have, because it's not necessary that we will be using our transistor in a small signal configuration all the time, right? So in that case, what you have to do is you have to find out what is the gate voltage, you have to find out what is the source voltage, right? And then you'll have to ensure VGS, whatever that VGS might be after solving KVL and KCL, is much less than twice overdrive. And if VGS is supposed to be a sinusoid, right? If incremental VGS is equal to some sinusoid, let's say some A sin omega naught t, AGS sin omega naught t, right? You'll have to ensure that AGS is much less than overdrive, right? This is for validity of small signal approximation. Now one might say that what is much less, whether 10 times less is much less or 100 times less is much less. That depends on the application, right? So the whatever you'll be designing a circuit for certain application, right? That application will have a specification what is this much less, and for you'll have to design your circuit based on the requirement of that particular application. Okay. So let's move on. So in now, if I ask you, if I give you a let's say a common source amplifier, right? The way we went about finding out the total currents and voltages in the common source amplifier in the previous lecture was to combine the incremental and the quiescent conditions in the same figure, right? And I walked you through the steps, but that can be a bit of a hassle when the circuit becomes a bit more involved. When you have multiple transistors, when you have multiple elements, right? It might not be so easy to draw or to sketch all the incremental and the total currents in the same figure, right? So what we generally do is we break the problem into two parts and then combine them in order to come up with a solution. Let me demonstrate that with the same example that we have been taking till now. So let's take what I'm basically trying to motivate here is that in the next part of this lecture, what we will do is we'll see how can we combine the incremental and quiescent conditions to get to total currents and voltages in the network. Right? So this is what we'll be focusing on in the next few minutes. Okay. So let's take the same example. Okay, so what is step 1? Step 1 will be find quiescent currents and voltages, right? So how will you find quiescent currents and voltages? You get rid of inputs, get rid of incremental inputs. In this case, the incremental input was only one voltage source. We get rid of them. When I say get rid of them, I mean I desensitize them, right? So voltage source desensitizing means it gets shorted. If I had a current source, I would have had to open circuit them, right? Okay, so now from this, what will I do? I will solve the full blown nonlinear equation, right? So how do you do that? Solve for I and V using KCL and KVL, using the nonlinear IV current equations of M1, right? So you will be getting, what you will be getting from this? You will be getting VGSQ, you will be getting all the parameters, right? You will be getting VGSQ, you will be getting VDSQ, you will be getting IDSQ, right? So we'll combine them. What is the next step? The next step is make the incremental model of the nonlinear network. What is the incremental model of that common source amplifier? We know that, we have done it sufficient number of times now. The incremental model of the common source amplifier is this, where there is no, we don't have any constant voltage or current sources. We only have incremental quantities, and the MOSFET has been replaced with its incremental equivalent. Vi, this is gate, this is source, this is drain, this is GM, VGS, right? So what will you do now? Now note that this is a completely linear network, right? So what will you do? We will find, so here we will be solve for I and V in the incremental network, linear network. And what will be step 3? Step 3 will be combine the currents and the voltages that you have gotten from step 1 and step 2, right? To get total current and voltage, combine the currents and voltages Let me also mark the figures, that would be helpful. This is figure 1. This is figure 2. Combine the currents and the voltages obtained from the quiescent analysis. So this is figure 1, and incremental analysis. This is figure 2, right? So what will you get after at the end of this? So from figure 1, we will get VGSQ, IDSQ, VDSQ, right? And from figure 2, we get small VGS, small IDS, small VDS. So what will be the total? Is small v, capital GS will be VGSQ plus small VGS. Similarly, IDS will be IDSQ plus small IDS. Similarly, VDS will be, this will be VDSQ plus small VDS. Okay. So once we have this framework, we can use this for any network, right? We can essentially close our eyes, find out, find out the quiescent conditions, convert the quiescent transistor circuit into its incremental equivalent, find out the incremental conditions, and combine those two. Now note that the incremental equivalent is related to the quiescent network, because in order to figure out the incremental equivalent, you need the values of GM, right? And what does GM depend on? GM depends on the quiescent condition of the primary network, right? So the value of the GM will change if you change the quiescent condition, but the analysis procedure or the steps that we go through doesn't really change. Okay.